Hi, my name is Jack Parker-Holder, and I'm here to present the paper Effective Diversity in Population-Based Reinforcement Learning. This is work by my collaborators Aldo Pacchiano, Krzysztof Choromanski, and Stephen Roberts. The key question we seek to address in this paper is, how can we effectively encourage diversity in a population of RL agents? Many existing approaches have attempted to tackle this problem. However, they almost always measure diversity using the mean pairwise distance between policies. This has two key issues. Firstly, it induces cycling, whereby agents repeatedly rediscover the same behaviors and never fully exploit them. Secondly, it can lead to redundancy, as we show in the diagram. On the left, agents are grouped into clusters. From a top-down view, the population may appear diverse, but has several policies with the same behaviors. On the right, we see a set of policies which can all be described by a linear combination of the others. Another key issue is the requirement for a hand-specified behavior characterization. For example, for a locomotion task, a popular choice is the final XY coordinates of an agent. This is intuitively appealing, but it requires human expertise for every individual environment. To start, we begin with some standard definitions. The main focus on this paper is a population of policies, where we use big theta. Now moving to our approach. We define the behavioral embedding as the actions taken by a policy for all states in the environment. If the policy is deterministic and the MDP is finite, then two policies are essentially identical if they have the same embedding. We define the pairwise similarity with a kernel, such as the squared exponential kernel. This allows us to define the population diversity as the determinant of the kernel matrix. This is similar to how subsets are measured in determinantal point processes. We call our approach diversity via determinants, or DVD. The key idea is that using the determinant focuses on the most similar policies, whereas pairwise distance is agnostic to where the diversity comes from. Here we have a simple example to illustrate what this actually means. On the left we show a simple MDP, with 4 states which require actions, which can be left, down, or right. There are 5 terminal states, 3 of which, in blue, have positive reward. There are 5 ways to achieve positive rewards. The agent can either go left, 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 right, down, down, right, left, or right, right. If we measure the diversity using determinants, we only get a non-zero value for the set of policies just described. However, pairwise distance can actually provide a higher value with duplicates. For example, if we remove the 0, 0 and replace it with another value. Now, a key component is the temperature parameter lambda, which trades off diversity and rewards. In our algorithm, we use Thompson sampling to select from a discrete set of values. This allows the parameter to adapt during training and removes the need to tune an additional hyperparameter. Now moving to practical implementations of DVD. The first is with evolution strategies. We consider the policies of the whole population as one long vector and perturb it as usual in ES, but then set the function value to be the mean local reward from each policy, plus the total population diversity. Since it's an ES-based approach, it can be trivially parallelized. We tested DVD ES on a variety of challenging problems. We compared versus a recent version of novelty search in orange and a simple vanilla ES in grey. On the left, we see a simple environment where DVD is able to escape deceptive rewards. On the right, we show the population is able to learn both tasks in a multi-objective problem, while the other 2 baselines are not able to do so. On this slide, we assess the importance of the adaptive mechanism. We show in 5 environments that DVD works more effectively with Thompson sampling than it does with an arbitrarily chosen fixed value. Now moving to our second algorithm, we applied our method to TD3, a state-of-the-art off-policy RL algorithm. Since it's off-policy, we can collect data with a population of agents and learn one shared Q function. We then optimize each agent with respect to the Q function, plus the population-wide diversity, which we show is differentiable. We tested DVD TD3 on the humanoid task from OpenAI Gym, where we show statistically significant gains versus both single TD3 and another version where we have a population of agents but no diversity. As far as we're aware, this is the first approach to get over 6,000 on humanoid in 1,000,000 time steps. Finally, here are some references on a variety of the topics covered in this talk. Some of these are presented at ICML, so they can be viewed this week. Thank you very much for your time.